Okay, so good morning to all of you. Yeah, so today we will be continuing our discussion on deriving the conservation laws. So we will again revisit some aspects of the momentum equation derivation, and from there we will continue and complete it, and then look at the derivation of energy equation. Okay, so let us look at the momentum equation, the derivation today first. Let us consider the control volume in rectangular coordinate system. So now we have to apply the Newton's law, which says that the force vector is equal to the rate of change of acceleration, the acceleration times the mass, so which is essentially required to balance all the forces which are acting on this control volume. And we already have expressed the total derivative of velocity in terms of the partial derivative, so we will equate both sides. Okay, so let us just quickly try to summarize the forces which are acting on this control volume. So essentially you have the normal stresses. Let us put our coordinate system origin as x, y and z. Okay, so we have the respective dimensions of this control volume as delta x, delta y and delta z. The we'll start with the body forces. The body forces acting are gx, rho g x, rho g y and rho g z. Okay, so these are the volumetric forces. So the acceleration, so this is the force per unit volume, so that therefore you have the gravitational acceleration times the density, and of course when you put these forces for the entire control volume, you have to multiply by the control volume to calculate the net force on this control volume. Similarly, when we look at the influence of forces, as we discussed, there are two kinds of forces. One is your volumetric force, which includes of course in our case the gravity. Number two are your surface forces. Okay, so these surface forces can be split into two categories. One is your pressure force and the other is your viscous forces, which include your normal and your shear stresses. So coming back, let us include all these forces on this control volume. So let us begin with the normal shear stress. You have sigma xx acting on this face on the left hand side on an x plane, and on the right hand side on the x plane you have sigma xx plus d sigma xx by dx delta x. Of course this is the stress, and to get the force you have to multiply by the corresponding area of cross section. So I am going to show only the forces in two directions, otherwise it becomes too cumbersome on this control volume. So you can extrapolate and include the forces in the third direction also. Similarly we have sigma yy, okay, and sigma yy, this is sigma yy delta x delta z, this is sigma yy plus d sigma yy by dy into, okay, so this is going to be delta y into delta x. Okay, similarly you have the normal stress in the z direction. Now coming to the shear stresses, now these normal stresses act in the direction of the area normals, okay, which point away from the surface. So if you include the pressure forces, which also act normal but they are compressive in nature, okay, so the pressure forces act in this direction, okay, and now the representation that I am using for sigma, okay, xx, this includes my pressure force and the normal shear stress. Okay, so this is the complete stress tensor that I am using to denote both the pressure as well as the viscous shear which is acting normal to the face. Okay, so similarly I will go ahead and include the viscous shear acting tangential to the faces. Now if you look at the notation, as I said, the second index here, okay, the last index corresponds to the direction in which the force is acting, and the first index is denotes the plane on which the force is acting. Okay, so if you want to, for example, say I want to calculate what is the shear stress acting tangential to this x plane on the left side. Okay, so let me say that this force is acting in the downward direction. You can also say the force is acting in the upward direction and you will get to the same result, but in our case we will say that this is acting in the downward direction. So this will be tau. So the last notation index should be y, and what should be the first? X. Okay, so corresponding to that, now this force should cause a turning moment in the anticlockwise direction. So this counterpart on the right hand side should be pointing upward. Okay, so this should be tau xy plus d tau xy by dx delta x, and once again this is a stress, you have to multiply by the corresponding area. So on and so forth. So similarly, if you consider a stress which is acting tangential on the bottom surface, so we will indicate this as tau. Can you say what it should be? Tau yx. Okay, and similarly on the top, so now this will cause a clockwise moment. Okay, so this should be tau yx plus d tau yx by dy delta y, and this should be multiplied by delta x delta z. Okay. So similarly you can fill up the other stresses. So totally if you put all these stresses together in a tensor form, you expand the tensor, you actually get a matrix, and these are the elements of the matrix. You have the normal stresses which include the normal viscous stress as well as the pressure. So this will form the diagonal elements of this matrix, and you have the tangential viscous stresses which act the off diagonal elements tau xz, and this is your tau yx, tau yz, so tau zx, tau zy, tau zz. Okay, so there are totally 9 components. So you have 3 normal components and 6 tangential components out of the 6. So I'll quickly show which are the other components acting on these faces, and you can fill the rest. So you have already 2 denoted here. So the other will be, you can take case where it is acting this way on the top surface, and this should be what? Tau yz, right. And you can also take a plane which is in the z direction, a z plane, and you can talk about a force which is acting in the along the x direction. So this should be tau zx. Okay, and you can also have the same z plane, you can have stress which is acting tangential pointing in the y direction. So this should be tau zy. And what else? So you have 1 2 3 4 5, so one more. So you can look at this left and right planes. So you can have again a stress which is acting in the z direction, right, on an x plane. So this will be tau x z. Okay, so this completes all the 6 viscous stresses acting tangential and the 3 remaining normal stresses which are acting normal to the surface areas. So with this we will go ahead and calculate what is the net force acting on this control volume. Okay, so we know the force acting on each face. So we have to say this the forces which are acting along the positive xyz directions are are the forces, the net forces in that particular direction. Okay, so we will calculate the net force, which gives you the left hand side part of this Newton's law. So let us calculate the net force in the x direction. Okay, so if you balance these forces in the x direction, what should be the net force? Of course, you have your gravitational force, okay, per unit volume. If you multiply by the volume of the control volume, that will be the net force acting on that control volume. And what should be the other shear stress terms? Plus d sigma xx by dx, okay, plus d tau yx by dy plus d tau zx by dz, and of course this has to be multiplied by delta x, delta y, delta z, right. So similarly the forces in the other directions, now you can fill them yourself. So the thing is this, if you look at your notation, you can see that the force acting along the x direction will have the stress pointed in that direction, and of course you have the gradient of these force in a particular direction in all the three directions. Okay, you have in the x direction, y direction, and z direction. So those have to be also accounted for. Okay, so similarly, if you look at the net forces acting along the y direction, you have sigma yy by dy plus del tau. So what should be this term right here? Xy by dx plus d tau zy by dz. So this should be the gravity in, this should be in the y direction, and this should be in the okay. So this consists of the net forces acting on this control volume faces, and we have also expanded the total derivative. So let us equate them, and before we do that, there is one more thing which I want to indicate, that although there are 6 of these viscous forces which are acting tangential, out of that we will use the identity that the forces tau xy should be equal to tau yx, and similarly tau xz should be equal to tau zx, and tau yz should be equal to tau zy. Okay, so this will reduce the number of unknowns from 6 to 3. Okay, so why this is required? I think I will leave this as an exercise for you. You can check, you can take the case of 2-dimensional control volume. Okay, you can balance the forces, and you can see for yourself that, for example, in this case you have tau xy acting here, you have tau xy plus d tau xy by dx into delta x, and bottom you have tau yx, and here you have tau yx plus d tau yx by dy into delta y. Now this, of course, the dimensions of this are delta x and delta y. Now if you want to make sure that there is no rotational movement on this control volume, okay, that comes from the fact that the acceleration, if you reduce your delta x and delta y, as delta x and delta y go to 0, so the acceleration of this, the angular acceleration that we are looking at, should not go to infinity. Okay, so if you denote the angular acceleration, so this is your angular displacement, and if you denote your angular acceleration as I am going to use the notation here as d square, yeah, alpha by dt square. Okay, so this should not go to infinity. So this condition can be satisfied only if there is no imbalance in these forces. So that should be possible only under this condition. Only if your tau xy is equal to tau ix, there will not be any imbalance which will rotate the fluid motion. Okay, and therefore at the limiting case where your delta x and delta y becomes a point, the angular acceleration shouldn't go to infinity. So under this condition this has to be satisfied, and which means that there is no rotation to this control volume caused by the imbalance of the forces. Okay, if you also implement that, I think now your number of unknowns in the stresses come down to totally 6 instead of 9, and we will expand the forces and equate them to the total derivative. The total derivative, we all know that we can write your du, for example, by dt as a partial derivative with respect to time plus the spatial derivatives like this. Okay, so on and so forth for the accelerations in the other directions as well. Now, so this is converting the Lagrangian framework to an Eulerian framework. So if you equate them to the corresponding forces in the direction, we can write this as so we have already mass into acceleration. Mass can be written as density times the volume. Okay, so we can cancel the volume in both the sides. So we will have rho du by dt should be equal to this term for the balance of the forces, which is rho gx. Okay, now what I am going to do is I am going to take out pressure from the notation sigma xx and retain only the normal component of the viscous stress. Okay, so I am going to say minus dp by dx, correct, plus d tau xx by dx plus d tau yx by dy plus you have d tau zx by dz. So on and so forth in the other directions. I think you can fill in the blanks yourself. So you can equate that to the summation of the forces, and now we are going to have to introduce some kind of an approximation to equate the forces in terms of these shear stresses. We have to rewrite them in terms of the known quantities which you are supposed to calculate and find out which are these velocities. Okay, so the velocities are the quantities which you fundamentally calculate. Okay, whereas the stresses are something which you don't know. Okay, so we have to equate the stresses to these quantities which you probably know after the end of solution, and so that's therefore there has to be a relationship invoked to equate the to relate these stresses in terms of the velocities. So that's what we are going to invoke this approximation as a Newtonian fluid. Okay, so one of the important, so far we have not invoked any great assumptions, right? We have considered all the forces, we have made sure we have balanced them properly, we have not neglected anything, we have not made any fundamental assumption here, except that we are working on a Cartesian framework. But now the first assumption is going to be that we will take consideration for a Newtonian fluid, and for a Newtonian fluid, so we have to write down the relation between the stresses and the corresponding strain rates. Okay, so these are given for a Newtonian fluid in the following manner. So your normal stresses sigma xx, you can write your pressure plus your normal viscous stress, that is your tau xx, which is written in terms of two coefficient of viscosities. Okay, so I am going to use the symbol lambda for one coefficient of viscosity. In fact, it is usually called the second coefficient of viscosity. Okay, so times the divergence of velocity. so which in Cartesian coordinate system if you expand it will be like this, plus you have your main coefficient of viscosity nu. Okay, so there will be a 2 nu du by dx. Similarly, if I go ahead and write the relationship in the other directions, you can write the same thing, the divergence term will be there as it is, plus you have 2 nu into, so can you guess what should be del v by del y. Okay, similarly if you write in the z direction, okay, so these are valid for a Newtonian fluid. And how about the shear stresses? Okay, so the shear stress can also be expanded in a similar form for a Newtonian fluid. So let me erase these portions. So we have tau xy. We have already shown that for inducing no rotational force on the control volume, this should be equal to tau yx. Now that is given as a relation between the stress and the strain rate as this, dv by dx plus du by dy. Similarly, tau xz should be, can you guess the terms here? So dw dx plus du by dz. Okay, good. So you have the final term. What is the final term? You have tau yz, tau zy, that should be nu. So this should be dv by, for example, dz plus dw by dy. So this is a closure. Now we got the closure problem and we closed it using the Newtonian fluid approximation, where we are relating the stresses to the strain rates by this. Okay, so this is also an approximation. If you work with non-Newtonian fluids, okay, then you cannot apply this kind of relationship between, that is, this is almost saying you have a linear relationship between the stress and the strain rate. Okay, now what are these lambda and nu here? Okay, so lambda denotes, if you come to this right here, so this nu, as you all know, this is your absolute viscosity, right? So this is also called as your shear viscosity sometimes, which you are all familiar with. When you say viscosity is the property of the fluid, you talk about the absolute viscosity or the shear viscosity. Now you have also introduced another coefficient here, which is the lambda, which is actually the bulk viscosity. This is sometimes referred to as the bulk viscosity. Also it is more commonly referred to as the second coefficient of viscosity. Okay, so there is still a lot of debate on the purpose of introducing these two viscosities and what is the role of the second coefficient of viscosity. Anyway, so in order to finally close this, you also need to, you know that mu is a property of the fluid, so you also have to introduce a relationship between the lambda and nu. Okay, so that is introduced by what is called as Stokes hypothesis. So we are introducing approximations one after the other. So the Stokes hypothesis states so this is an hypothesis, you know, it is you can see it from the name, you know, Stokes hypothesis means, you know, people have not exactly verified it. It's mathematical convenience to reduce the number of unknowns. And what Stokes says that if you introduce the fact that 3 lambda plus 2 nu equal to 0, that means your lambda is equal to minus 2 by 3 nu. Okay, so this will give you a nice form of the relationship between sigma and the strain rates, convenient to suit your things to simplify a little bit. and in fact when we do that we can also rewrite, we can now plug in for these stresses in terms of the strain rates. Okay, now I am going to rewrite them in terms of the strain rates rather than the stresses. So for the x momentum I will replace the derivatives of these stresses in terms of the strain rate. So I can say d by dx, okay, so nu into 2 du by dx minus 2 by 3 into del dot v, so which is the divergence. The divergence is actually given by this term right here, this is the del dot v term, okay, and 2 by 3 comes because your lambda is equal to minus 2 by 3 nu, okay. Apart from that you also have your du by dx, 2 nu du by dx, okay, that is essentially coming from this term right here, okay. So I am just grouping the terms under the normal stress, okay. Similarly if you expand that in terms of shear stress and write in terms of the strain rates, you get d by dy into nu. So what should be the term? So you have your tau xy is equal to tau yx, so I can write this as d by dy nu into what, dv by dx plus du by dy. So I can also go ahead and complete the third term, d by dz of tau zx should be equal to tau xz, that will be dw, that is nu times dw by dx plus du by dz. Okay, so it's a very lengthy expression. So this is the x momentum equation, so which is coming to a more familiar form, right? So if we started with putting the stresses, and now we have invoked the approximation of Stokes and the Newtonian fluid, and finally we are writing this in terms of strain rates. So we will simplify one by one gradually. So we will write the y momentum equation similarly. You have rho dv by dt, so that should be rho gy minus dp by dy, okay, plus d by dx of, can you tell me the term that should come? Nu into, there should, is there a 2 here for the y momentum? What is the term corresponding to d by dx in the y momentum? Tau yx, right? So tau yx and tau xy are the same, okay. So this should be dv by dx plus du by dy, alright, plus, so d by dy, so now you have your normal stresses, okay. So you have nu into 2 dv by dy minus 2 by 3 divergence of velocity plus you have d by dz mu into dw by, is it dw by dx, dy plus dv by dz, okay. So you can write the z momentum similarly. I'm not going to do it. I'll give you a couple of minutes to write down the z momentum also the same manner. Yes.
The Stokes hypothesis, which has been shown right now, has it been experimentally proven at least to be found close to the actual value? Like, is lambda found to be close to minus 2 by 3 mu? Because we can't simply accept such a.
Yes, that is true. Well, Stokes hypothesis has not been proven directly, but the final reduced form of the Navier-Stokes equation, which you get after invoking the Stokes hypothesis, is definitely agreeing very well with the experimental data. Okay, so that shows that Stokes hypothesis is pretty good. Now Stokes, when he showed the hypothesis, he didn't do experiments to confirm his hypothesis. He just proposed based on some intuition and based on the structure of the Navier-Stokes, and later when you use this equation and solve them entirely, so you are seeing that you get very good agreement with the experimental data. So that itself confirms. Okay. Okay, so now I hope that you have completed the Z momentum. Now what we will do is, this is still not the simplified form of the Navier-Stokes that we would like to use. Okay, and as I said, we will be focusing on primarily incompressible flows. Now this is valid for both compressible and incompressible flows. We will introduce another approximation that we will be looking at only incompressible flows. So for that, you will see that magically many of the terms drop out, especially the divergence term should drop out because it satisfies the incompressible continuity equation, right? So you have your divergence term which drops out from all these equations, and you can also group the terms in such a manner. So here for example, okay, if you look at this terms right here, okay, you can write this as d by dx of dv by dy, plus you have d by dx of du by d by dy of du by dx, plus you will have similarly d by dw by dz into d by dx. So all these terms, once again you can take d by dx common, and you have du by dx plus dv by dy plus dw by dz. So that will again satisfy the incompressible continuity, that will drop out. So finally when you retain only the necessary terms, you will have rho du by dt is equal to rho gx minus dp by dx plus nu times d square u by dx square plus d square v by dy square plus d square w by dz square. So this will be your x momentum. Your y momentum will be so this will all be u in terms of u, I am sorry. Okay, so this will be in terms of v. Okay, so I think you can relate and verify the terms once again. Okay, so you should have this term knocked out, and then you have d square u by dx square, you have d square u by dy square, you have d square u by, so you can take d by dx of du by dx, dv by dy, dw by dz, which will disappear. So from each of these momentum equations you will have you will satisfy continuity here as well as if you group the terms together like that. Okay, so hope all of you got it. Okay, so the remaining terms will just be the Laplacian operator. Okay, so this is the more familiar form, I guess, correct? When you start with the analytical solution of equations, you are more used to this form, right, for incompressible flows. We can write also this form in terms of a coordinate free representation. That is what we want to do if you want to apply this in all the coordinate systems. So in a coordinate free representation, so we can write this as dv by dt, and v is a vector here indicating velocity in any direction. That should be equal to, I am dividing throughout by rho, so that will be g vector minus 1 by rho into, how can I write the pressure gradient, del p okay, and the term here d square u by dx square and so on and so forth, this is nothing but the Laplacian operator del square and the corresponding v vector. So this is a very compact notation which indicates the momentum in any direction that you consider and in any coordinate system. You have to use the corresponding the derivative operator as well as the Laplacian operator in that particular coordinate system, and you will write those equations in either cylindrical or spherical coordinate system. Okay, so what we will be doing mostly in our course is we will be focusing on the incompressible form of the Navier-Stokes equation, and we will also apply this to two-dimensional flows. So therefore the third derivative will all be neglected. Okay, so that will be the compact form of the Navier-Stokes that we will be considering. So with this we have completed the momentum equation derivation. Very quickly let me start the energy equation derivation, okay, which is more important because you have probably gone through the momentum and continuity in your earlier courses also. Any question on the derivation part? I think it's very clear, right? You have already done it, so it's just a reconfirmation of what you have learned. Let us start with the energy equation. Now once you understand the momentum equation clearly, I think the energy equation just follows, only you should know the contributions to the energy. Okay, what are all the components of the energy? So let me erase okay. So when we come to energy, we have to be very clear what is the balance of energy that we want to do. So once again, just like we have a mass balance, we will write down the first law of thermodynamics for a control volume. So which is nothing but the energy balance, okay. So what does the first law of thermodynamics say? For an open system, the rate of change of energy within the control volume should be equal to the net efflux of energy across the control volume boundaries, okay. So this is a very compact way of phrasing the first law. Let us expand upon the term efflux of energy. So there are many contributions to that. So what it says clearly is that your rate of change, I am not using notations right now, I will introduce the notations one by one. Rate of change of energy in a control volume should be equal to your energy in or rate of energy in minus rate of energy out, okay. So this is represented in rate terms, so therefore I should say rate of energy, right, energy which is instantaneous. So per time, in a given time, the energy which is basically crossing the control volume boundaries. Now when I talk about this is nothing but the efflux of energy, right, totally. So this is your energy efflux, okay. So now this efflux of energy has the following components, okay. So let us look at first the energy and its constituents. You can use the notation E to denote energy per unit. Should it be per unit volume or unit mass? Per unit mass, okay. So that should have contributions from what? So suppose if you look at the energy of a system, so the total energy has contributions from its internal energy. Let me call that as U. This is the internal energy per unit mass, plus you have the kinetic and potential energy terms, okay. So I am going to put the kinetic energy term here, U square plus V square plus W square by 2. This is also, these are per unit mass, Okay, so what I am going to do, I have not included the potential energy term here because I am going to consider potential energy term under work. Okay, because already you have the forces which are acting on the control volume and they do some work, and gravitational force is one of them. So I am going to consider that as a part of the work rather than as a part of the total energy contributing to the temperature of the system. Okay, so anyway it will all come in the balance of energy, so it is not lost anywhere. So this is the definition of energy I am going to use. So therefore, so the initial energy of the control volume will be what? So if I know this is the energy per unit mass for the entire control volume, what will be the energy into mass? So that will be density times the volume times this energy, right? So rho E into delta x, delta y, delta z, right? So this is going to be the energy possessed by the control volume at some starting time from which you are calculating the change in the energy after a time delta t. Okay, so the final energy of the control volume after some time delta t, you want to see what is the energy at that point. Okay, so that will be rho E delta x, delta y, delta z. And so how should I, so I should use the Taylor series expansion. Okay, if I think that the time is infinitesimally small, I can write the Taylor series expansion, right? So plus d by dt of rho E delta x, delta y, delta z into delta t. Okay, so therefore your rate of change of energy of the system will be your final minus initial so your so that will be what, d by dt of rho E, okay, and multiplied by delta x, delta y, delta z, delta t. Now where your E is expanded into constituents of internal energy and the kinetic energy in that manner, so I can also write this as d by dt of rho times u plus u square plus v square plus w square by 2, okay, into delta x, delta y, delta z. So this rate of change from, no, you are calculating at later time minus the initial time. Okay, so yeah, if you have energy which is depleted, it will be negative. If you have energy which is gained, it will be, rate of change will be positive, right? Okay, so this is the rate of energy, change of energy, which we are balancing on this on the left hand side with the energy efflux terms. Now when you look at the efflux of energy, the net efflux of energy, so you have components of what? So what are the things which can come in and leave the control volume? So one is the components of internal energy and kinetic energy itself can be carried by advection process. Okay, so you have efflux of your kinetic energy, your internal energy, right, due to advection. Okay, and you also have components of what? Apart from the components of the energy which constitute the total energy of the system, what else can change the energy of the control volume? Conduction, so that is basically a heat transfer process. So you can have heat transfer which is happening along across the control volume boundaries. You can also have work transfer. Okay, when you talk about energy, you have both components of heat and work. Okay, so you have efflux of these. Also you have plus you have efflux of heat. Okay, now efflux of heat is not happening due to advection. Okay, it is purely a diffusion process or a conduction process. Okay, so plus you have efflux of work. And now how efflux of work is happening? Already you have these forces acting on the boundaries, and so they do some work on the control volume boundaries. Okay, now the contributions of each of these. Now efflux of internal and kinetic energies is easy to write, so I am just going to write it down. So can you guess how the structure of efflux of internal and kinetic energy should look? So it is like I am saying, if you take this control volume, you have the flux of internal plus kinetic energy which is entering, for example, on this left x plane, and on this side this will be rho u internal plus kinetic plus d by dx of rho u internal plus kinetic into delta x, right? You have entire thing multiplied by delta y delta z. So similarly in this direction, you can also write this as rho v into internal plus kinetic energy into delta x delta z. This will be rho v alright. So similarly in the third direction you can write it. Apart from the efflux of the energy of the system, efflux of the energy which is coming due to advection, you also have the heat transfer. So you can say this is probably qx, that is the heat flux which is crossing this particular left x plane in the x direction multiplied by delta y delta z. Okay, so this is the heat transfer rate in this direction. So on this particular plane this will be qx double prime plus dq x double prime by dx into delta x into delta y delta z. Okay, so I will probably erase. Okay, similarly you have conduction of heat in the other directions as well. So I am representing heat flux in this direction into delta x, delta z will be the heat flow rate or heat transfer rate, and similarly you can express this as and also in third direction you can do the same. Apart from this you also have work transfer, okay, which you can write it down. So work transfer in both the directions, okay. So now, so this is the complicated part of the derivation of energy equation. You have heat transfer rates, you have work transfer rates, you have flux of energy, everything coming into the control volume and leaving at the same time. So you have to balance all of them in one single equation. So that's why it gets a little more tedious than the continuity and x momentum, and because the momentum as such is directional, so you can very easily balance in each direction, whereas here you have to include all the contributions into one single equation. Okay, anyway, so we will stop at this point and tomorrow we will continue, and this is from the Eulerian point of view. We will also do a derivation starting from the Reynolds transport theorem, which is completely coordinate free and it connects the Lagrangian to the Eulerian. So from there we can reach to the same conclusions. Okay, so thank you so much.